All right, welcome back. I'm excited to introduce our next speaker, Suhas Sreehari. He is the Assistant Vice President at Wells Fargo. Please join me in welcoming him to our virtual stage.
Thank you. I'm excited to be here, and we have some incredible material to talk about. It's going to be about 15 seconds before I share my screen. All right, there we are. Thanks a lot for joining. I know it's been a stimulating day, and this is going to be somewhat different from some of the things we've heard, but I think it's fascinating. The issue with a lot of machine learning we do is that we are constantly looking for algorithms that do better predictions, that have various performance benchmarks. The thing that we don't talk a lot about, and slowly it's improving, is the aspect of explainability. And in particular, we don't have a formal analysis to understand the balance that needs to be struck between generalizability and explainability. When I say when I say generalizability, what I mean is the ability to extend the performance that you see when you train a machine learning model like a neural network to data that you have not seen before. Now, there are two kinds of them. One is data which is drawn from a similar distribution that the training was performed on. And then there is data that comes from a totally different distribution. And the latter is usually typically much harder to solve. So we're just going to focus on data that comes from the same kind of distribution. So before we actually get into the topic, I just want to briefly outline some of the challenges of machine learning from my perspective, the way I see it at Wells Fargo, and the way I see it with my interactions with my collaborators. I have people that I worked with in industry, in national labs, in academia. So this is sort of the consensus opinion of the current problems we face with machine learning. The first thing is explainability, and this is going to be predominantly the topic of my talk. And there is a sentiment that output is not enough. Now, what do I mean by that? So you have this algorithm that has amazing metrics. It has an AUC of 99% or 0.99. It has very low RMSE values, and it has very high precision and recall. All right, so it's great, but the thing is we still don't know why it makes some predictions or estimations that it does. So that really becomes a problem, because it goes back to this old saying where it goes something like, you teach a man how to fish, you fed him for a lifetime. You give a man a fish, you fed him once. So that is really true with machine learning too. So as long as you have a good model with you that works, that's not broken yet, and it keeps working, you're fine. And the minute something happens, you get new data, or or the model breaks somehow, we go to a corner case, then we're totally at a loss because we haven't learned anything from it. And this is where explainability comes in. And also, I'm going to show you one example at the very end of my talk as to how explainability can actually guard us against adversarial attacks in machine learning, where you change the data ever so slightly, and especially for classification problems, and the algorithm classifies the input to be something very, very different. And then there is the, okay, so that's the explainability part. Then there is the question of uncertainty quantification, which essentially tries to answer the question, is there uncertainty in the prediction that we have from the machine learning model? Well, yes, we do. But then the issue is, do we know how to quantify it? Is it large enough, or is it small enough that we can actually live with it? And now that depends on the application. So we've got to tie in with the exact task that we have, and then see if the uncertainty is still doable. That is a much different problem. And then, although people do talk about UQ all the time, I think it's one of the underexplored areas. And we're not going to talk about it today. The last one is data, right? Because majority of, I don't have the statistic on this, but a majority of um, the learning that happens within these algorithms is supervised. At the minimum, that's how it is because, okay, so here's another cue for it. My Wells Fargo email is that they do that big label data. And so we need a lot of data. And the problem is we don't know what a lot means. So again, there's no quantification for how much data a particular model can do with or cannot do with. And data might be noisy or unreliable. We don't know a lot of times how to do variable transformations. So there are a lot of data aspects to the challenges. Again, we're not going to talk about it. But the good thing about this is the most explored part of ML. So a lot of people have worked on it in various different ways. Okay, so back to our topic. What we want to do today is look at a neural network. And in particular, I'm going to look at a convolutional neural network because that's, I mean, you also have convolution as part of the neural network. And the idea is that if we deal with that case, when we want a simple neural network, we can just delete the convolutional part and still have a working model for it. And okay, this is AI for finance. And there's a reason I'm talking about convolutional neural networks. Typically, CNNs are used for things like image recognition, classification. When you have a car that has an autopilot, it typically has a large convolutional neural network inside it to understand the conditions of the road and things like that. So why are we talking about such a network for financial models? It's interesting because I'm trying to build up on my own work that I've done in the past, where you have a numeric vector or data set that we typically have. So let's say it's an M by N matrix where you have M customers or M transactions, and then you have N features per transaction. And now, if you look at this matrix, it's just, it looks like, you know, uh, garbled numbers, right? And typically you can't make anything out if you just look at it. So one of the previous things that I've been interested in and that I worked on is how you can actually push each vector from that matrix of your transaction database into an image. And specifically my previous work, I worked on using a pre-trained GAN and codifying all of these financial transactions as a noise vector for the GAN, which produces the output, which is an image. So for instance, you could train the GAN on a set of pictures of dogs. And what would then happen is each transaction would be codified as a picture of a dog or a puppy or something. And what interesting thing happened is, this was very surprising, is that when you have an anomalous transaction, so I work on anomaly detection. So when you have an anomalous transaction, the image that is corresponding to it in the GAN domain might actually be a strange image. For example, you might have a dog with half a tail or with no tail at all, and when you see that, you're like, huh, that's funny, because that is probably an anomalous transaction, and a lot of times it is. So once we codify a numeric transaction vector into an image, now we can start employing things like convolutional neural networks, and we can harness the power of these models. Okay, so that is the philosophical background of why we're talking about this. Okay, now the anatomy of a convolutional neural network, let's start with the neuron and the way I represent it. And let's say these are x1, x2, and xn are all the inputs. So these are the features. And then all of them are pulled in together through a weight, the W1 through Wn, into this orange or into this brown block here. And sigma and B, okay, so the brown thing at center is the neuron, is the artificial neuron. And it has two parameters. It has sigma, which is an activation function, and B, which is a bias. So then what that means is the output takes a form. So the sigma here let's, for simplification for today's discussion, think sigma is actually a sigmoid. Okay, so if you don't know what a sigmoid is, it's essentially something like 1 over 1 plus e to the negative x, where x is the argument. In this case, it's going to be 1 over 1 plus e to the negative, well, b plus summation of wi xi. In any case, the hyperbolic tangent or tan h and sigmoid are very similar functions. So it's just a matter of shifting and not even shifting, just scaling. So you go from one to another. So you could also, another typical choice for sigma is the ReLU function, which is the rectified linear unit. And we're not going to use that now, but it's easy to extend it to it. Okay, so now you have a bias and plus the summation of the weighted inputs. So that forms the input to the neuron. And so once, so what this means now is once the argument here, b plus the summation, wi xi, if that's bigger than 0, the sigmoid function actually pushes the value of y very close to 1. So higher the value of the argument, closer y gets to 1. And when the argument is negative, y typically gets very close to 0. Let's just say, well, it could be very close to -1, but you can always scale it so that it gets close to 0. So you have a 0 to 1 system, 0 to 1 scale on y. And therefore, a lot of times it acts as a probability score. So this is where it comes in. So the output of your neural network is between 0 and 1. So that could act as a probability. Sometimes it doesn't have to be. So especially when you use something like a ReLU function, which means that when the argument is positive, the output of the ReLU, or y, would be exactly that argument. So in that case, the output y can grow beyond 1. So it's not a probability anymore. And at that point, usually people have another layer in their neural network called a softmax layer or softmin layer, depending on what you want to do. And that kind of pushes all these numbers back to a 0 to 1 format from which we can make classifications again. Anyhow, at the bottom, I just want to spend more time with the background so that then we can like zip through some of the concepts. Okay, and so at the bottom, we see the neural network. So we see two layers of a neural network. My convention is going to be like this. The black dots are going to be the numeric values. So yk minus 1, okay? So that is the output of the k minus first layer of the neural network. We don't see the k minus first layer in the picture here, okay? We assume that's happened. And then there's a layer of neurons, and then there is the kth output, and then there's another layer, and so on. This is the general structure we're going to have. And this need not be a fully connected neural network, and right now it is not. Okay, so why do we use convolution? Convolution is, the first time I read about convolution in the neural network context, it was a little confusing because it's not really convolution. Convolution in signal processing has this idea that you have two signals, and then you flip one of them, you multiply, and add. And so per that definition, it's a little different. But what convolution is let's say you have an image. So remember, we have a financial data set, and each customer transaction, let's say each observation, each sample point is converted into one image now, okay? Somehow using something like I said, like generator adversarial networks or something like this. So this is, let's say on the what I have on the left is a portion of one of those images. So it's a portion of one of the transactions. And these are the pixel values or intensities, 0, 8, 2, 1, 1, 7, and so on. Now, the way you do convolution is you've got to figure out a kernel or a filter, which is which are these brown pixels. And assuming we already have a neural network that has been trained so that you understand what the kernel weights are. So if you look at the brown pixels, 1, -2, 0, and 1, these already have been figured out by the neural network in the process of training it. What we're trying to do is we're not training a neural network anymore. In this talk, we already have a neural network that is trained, and we are trying to distill it into a set of decision trees so that we can explain it better, okay? So we already know the kernel. And so we take 2 by 2 patches, if that's how big the kernel is. We take the similar size patch. We extract all of the 2 by 2 patches from the image. And then we actually do an element-wise product of them. So 7 times 1 is 7, 2 times -2 is -4, and so on. This is called the Hadamard product. And then we take the sum of it, and you get 7. So, so this block is now replaced by this one number 7. The image doesn't shrink because then the next block you would consider is this one, 2, 3, 4, 3. So you always have an overlap. It's called a stride in when it comes to convolutions, but you can control the stride so that you always have an overlap of all these patches. And so even though one number replaces 4 numbers here because of the overlap, you're going to get back the image roughly of the same size, except at the border sometimes. You can do 0 padding, or you can do whatever you want to fix that. The next idea is pooling, where okay, so this is the one where you actually reduce the size of your image. And you do that, one, to reduce dimensionality, the other to induce some sort of shift invariance. Okay, so basically the green quadrant goes to one number, the blue quadrant goes to another number. And how you can do that is you can either take the max or the min value or the mean value and then pool it together here. So this is self-explanatory. Okay. So the question is, can we build decision trees that mimic? And what can we expect in terms of generalizability, and how much insights are we going to gain? So it's the same model. So this is the way we model one neuron. What we do is we look at all these products, weighted inputs, Wi, Xi, and then we make a descending order sort. We sort these Wi, Xi or Wj, Xj such that they go in descending order. And now we redefine the variables and say Vi is defined to be Wi, Xi, where W's are the weights and X's are the inputs. Okay, so what that means is V1 is bigger than V2, which is bigger than V3, and so on. And so here's the equivalent decision tree. You have all the data that comes in, and then you check if the biggest combination, if the biggest weighted input you have, which is now V1, if that's bigger than minus B. So what happens if that's true is if V1 is bigger than minus B, then this term is already positive. It doesn't even depend on the other V's, because V1 is the biggest of them all. And okay. So if yes, you have an expression. So it's the expression for the approximate value of y is given by this node. So you have b plus v1 plus, you assume something like, you assume there's a constant and you multiply the constant value by the number of terms remaining. So we have totally n inputs, and we looked at only one of them, which is v1. And so there are n minus 1 remaining. We're just going to use an approximate multiplier to get the value of n minus 1. And the sigma of that for one node, which makes our computation very fast. And then, well, if v1 is not bigger than minus b, then we check if v1 plus v2 is bigger than minus b. And then if that's not true, then we check if v1 plus v2 plus v3 is bigger than minus b, and so on. So that is the decision tree view of one neuron. And then we can model an entire layer with decision trees. What we do is we usually go one horizontal row at a time. So the first neuron all the way through different layers is how we model. And let's say there is a layer of values, yk, and then we want to go from yk, that's the center layer, to yk plus 1. We can assume that there is a set of trees, decision trees, excuse me, which we call tk. And okay, now we can actually represent convolution. How do you represent convolution? We just need to represent convolution using a decision stump, sorry. Sorry, Trump is still on my mind. I know we're in 2021. Anyway, so what we do is we look at the Hadamard product between the pixel values and the kernel and check if that's bigger than 0. If that's bigger than 0, that is the output y. And if it's smaller than or equals 0, the output is 0. Why is it important? Because there is a chance that sometimes if you want to analyze these networks during training, we might have the filter values to be largely negative sometimes, which leads the Hadamard product to be negative. And but the Hadamard product is still an image. It doesn't make sense for an image to have negative pixel values. So you want to zero them out. That's what the 0 is for. That's guarding against that possibility of having negative images. Anyway, so so this is the decision stump I'm talking about, which means that there's only one layer in the decision tree. And so this performs the convolution for us. And we have a similar thing, a similar decision stump for pooling, where you only have, let's say, 1/4 of the number of pixels you have before you pool. So if you look at this image here, all the grayed out neurons are the ones that actually that we're going to ignore. So basically, when you pool, there are values that actually disappear. So instead of actually making it disappear, what we do is, in order to keep the dimension the same, because the TK decision tree, if it's a function that has an Rn to Rn mapping, it's easy for us to do the math and keep the same form of decision tree throughout the network. So we still want to keep those neurons and those outputs. We're not going to delete them, but we're going to set a negative value to them so that the algorithm understands to ignore them. That's how it knows that the non-negative values are the ones that are pooled. Okay. Okay, so we can do that. And then we can have a sequence of decision trees, because now one decision tree takes you from one neuron to another neuron in one layer. Now we have multiple layers, right? So we need we need a sequence of these trees now. And so here's in the right side, you see the tree structure for neuron 1 of layer 1. And then the dark green leaves here of the decision tree, that's where we actually continue the process and append a different decision tree for like a neuron 1 of layer 2. So that's how it continues. And both of these blue trees here, they are the same, but they are coming from different regions or from different leaf nodes. And then once you do that, then you do the same thing. You take, this actually is true for all the 4 different leaf nodes that we see here, but I don't have space to do them all. So you're going to have 4 different yellow tree continuations for layer 3. So you have tk minus 1, tk plus 1, tk plus 2. So you have a string of decision trees for every single neuron. Okay, so this represents one row. Okay. All right. I think I have about 5 minutes left. Okay. Okay. So this is the structure. So each layer is represented by a decision tree. And okay, now what? A lot of you are familiar with Shapley explanations. So we can use Shapley to understand, and now we can figure out why adversarial attacks happen. And there's a panda that's misclassified as a gibbon, and we know exactly why, because now we are able to use CNNs and Shapley together. That's about it. So this is
Awesome. Thank you so much, Suhas. Thank you for sharing with us. We really appreciate these insights. That was awesome. If you could stop sharing your screen, the audience is giving you a huge virtual round of applause. All right, if you're looking for your next session, go ahead and check out your agenda. And along the way, make sure to accept your connection request and check out our awesome AI exhibits. Thank you so much, and we'll see you around.